The title of this video declares the end of aluminum. It might come across as over the top or even a bit wild, but once you watch through to the finish, you'll see precisely why we chose those words. And you'll be nodding along. Because what Xiaomi has done to automotive manufacturing makes conventional aluminum feel like a relic from the past. Picture this. It's 2021. A brand known for affordable smartphones, kitchen gadgets, and electric scooters steps into the industry spotlight and announces, "We're entering the car business." Not just any vehicle. A machine capable of setting records at the Nürburgring ahead of a Porsche. A vehicle with chassis rigidity surpassing a Bugatti. A car whose structural sections are formed, not welded, in under 2 minutes each. The skeptics chuckled. 3 years later, the laughter stopped. The Xiaomi SU7 Ultra is here. It's real. It's driving on public roads. And it just completed the Nürburgring lap in 6 minutes and 46 seconds, edging out the Porsche Taycan Turbo GT by a noticeable margin. Yet the most mind-blowing aspect isn't the lap time, it's the construction method. Xiaomi didn't simply create another quick car. They discarded a century of conventional practices and began with a blank slate. No classic spot welding, no pressing and assembling countless steel panels, no enormous heat ovens. They harnessed artificial intelligence to create an entirely new alloy never seen before, engineered a colossal machine the size of 2 basketball courts to form it, and integrated the battery pack itself as the vehicle's core structural frame. The outcome feels like stats pulled from a high-end simulation. But every figure checks out. Every detail is proven by equipment already operating in their Beijing facility. By the end of this video, you'll see exactly how they achieved it and why legacy car makers are racing to keep pace. Let's go back to the start. The flaw in every car ever produced. Most drivers never consider this. But today's vehicles are assembled using methods that haven't changed much since the 1950s. Flat metal sheets get pressed into forms with massive machines, then joined by welding. Hundreds of components and thousands of connection points. It's the approach used for decades. Imagine building a cardboard box. You cut flat panels, bend them, and seal the edges. It gets the job done. But each bend creates a potential weak point. Each joint becomes a spot where issues can develop later. More components mean added mass and complexity. In vehicles, every weld represents a possible long-term vulnerability. A typical chassis might consist of hundreds of pressed elements joined by hundreds or thousands of welds. Each adds mass. Each introduces minor vibrations. Each can let unwanted sounds into the passenger area. For years, specialists have trimmed ounces here and there, refined steps, and cut minor costs. But the core concept remained unchanged. Then, EVs arrived and amplified the challenge. Electric cars must haul a large, heavy battery pack. The logical spot is beneath the cabin floor. Yet bolting a massive battery enclosure underneath turns it into non-structural mass. The vehicle grows heavier, demanding a more robust frame to support it. That extra frame weight requires even more battery capacity, which adds further mass, creating a vicious cycle. Tesla made a smart attempt to break it. Rather than joining many small steel sections, they began casting large single aluminum pieces using huge molds. They named it gigacasting. Dozens of welded parts became one solid casting, reducing joints, cutting weight, and speeding up assembly. It marked real progress. But a major limitation lurked within the material. This issue prevented widespread adoption by others, and overcoming it marks the true start of Xiaomi's breakthrough. The heat treatment barrier that held everyone back. Casting molten aluminum into a mold and letting it cool creates a solid-looking piece, but internally, it's relatively fragile. At the microscopic level, the crystal formations are disorganized and randomly oriented. The component appears fine, yet real-world loads can cause cracks or bending. The usual solution involves heat treating. placing the cast part in a large industrial furnace and heating it intensely for hours. This aligns the internal crystals, turning a brittle piece into one that's durable and resilient, like going from soft dough to a finished baked loaf. Same base materials, transformed outcome. Simple enough on paper. Here's the harsh reality. Heating a large, intricate metal section to those levels doesn't only strengthen it, it also shifts and distorts slightly in critical ways. For a precision chassis, where every millimeter counts, even minor warping misaligns parts. Doors won't fit properly. Suspension mounts shift. The entire assembly turns problematic. So companies faced an unpleasant choice: skip heat treatment for accurate shape, but insufficient strength under stress, or apply it for strength, but accept slight distortion. Every big manufacturer explored workarounds. Few cracked it. Many researched for years before settling for compromises, adapting workflows around the constraint. It became an accepted industry limitation. Xiaomi examined this and rejected the status quo. Their team reviewed every commercial aluminum alloy. None delivered the full mix of strength, flexibility, dimensional stability, and heat treatment-free performance. The ideal material didn't exist on the market. So rather than compromise, they created exactly what they required. The method they used ranks among the story's most fascinating elements: the artificial intelligence that created a new alloy. This is where it gets truly remarkable. Xiaomi developed an advanced AI platform called the Material Genome. Picture a tireless researcher that operates non-stop, runs countless virtual tests at once, and never tires. They supplied it with all available knowledge on metallurgy, alloys, and materials engineering. Then they assigned a clear goal: discover an alloy formula delivering high strength, good flexibility, excellent precision, and no need for post-casting heat treatment. The system simulated over 160,000 unique alloy combinations, actually millions in total across scenarios. That's hard to grasp. A human expert testing one new formula daily, year after year without breaks, would need more than 27,000 years to cover the same ground. The AI completed it rapidly. It explored combinations of aluminum with silicon, magnesium, rare earths, and other elements through vast digital models until finding the precise mix that satisfied every requirement simultaneously. Compare it to perfecting a chocolate chip cookie recipe. Instead of trying a handful of batches over weekends, you run millions of simulations accounting for every ratio, temperature, and timing variation. The system hands you the flawless formula instantly. That's Xiaomi's approach, but for atomic-level metal design. The outcome is their patented Titan's metal alloy, exclusive to Xiaomi. After casting and cooling, it emerges fully strong, dimensionally perfect, and assembly-ready without further processing. No furnaces, no distortion, no trade-offs. Production lines run quicker, use less energy, and achieve superior accuracy compared to traditional methods. Parts mate more cleanly. Tolerances tighten. One material breakthrough lifts the entire process, but an advanced alloy is only part of the solution. You still need equipment to deploy it effectively. And Xiaomi created something that feels almost unreal: the system that forms entire car structures. Tesla's Giga Press delivers around 9,000 tons of clamping force. When unveiled, experts called it the edge of current engineering capability, a machine that leaves seasoned professionals speechless. Xiaomi developed a 9,100-ton hypercasting machine. It's not merely a higher spec. This unit spans the area of 2 full basketball courts. It weighs over 1,000 tons alone. It heats the Titan's metal to 700 C and injects it into precision molds at velocities so high that air pockets can't develop during filling. Those air pockets matter more than you might think. Trapped bubbles act like hidden defects. The exterior looks flawless, but under performance loads, they initiate breaks. Ultra-fast injection creates the dense, void-free internal structure typically reserved for aerospace parts. every millimeter is fully solid. In actual production, consider the rear underbody, a critical structural area. Traditional builds use 72 separate pressed steel elements joined by 840 weld points. Each piece requires separate fabrication, shipping, storage, positioning, and welding. The full sequence takes hours and many operators. Xiaomi's hypercasting forms the equivalent section as one unified piece in about 100 seconds. 72 parts become one. 840 welds disappear. Hours shrink to under 2 minutes. Plus, the single casting weighs 17% less than the multi-part steel equivalent and reduces interior noise by about 2 decibels, since there are no vibrating joints or gaps at speed. Each casting is immediately inspected via X-ray and precision lasers inside the machine. AI quality control flags any defect instantly and rejects the part automatically, far beyond human inspection speed. Fresh structural sections emerge every 90 seconds. If you think that's the highlight, wait until you hear about their battery approach. The battery that forms the vehicle's frame. In nearly all current EVs, the battery is a large, costly, heavy module attached below the floor. It stores power, but contributes nothing to structural integrity. It remains passive added mass. Xiaomi posed a fundamental question. What if the battery wasn't just cargo? What if it served as the backbone? This drives their CTB Bobby design. Battery cells integrate directly into the chassis. The pack's upper surface becomes the actual cabin floor under your feet. The cells don't only hold energy, they actively reinforce the vehicle's structure. Xiaomi took it further with a clever reversal. They inverted the battery cells. Each cell includes a pressure relief valve for safe venting during overheating. Normally, these face upward toward occupants, requiring thick shielding layers that add height and mass. By flipping them, valves point downward toward the ground, away from passengers. Protection remains, but now the vehicle floor itself manages it, eliminating bulky internal padding. This slimmed the entire battery plus floor assembly to just 120 about the thickness of a hardcover book. Benefits are huge. The car rides lower than many pure sports cars, lowering the center of gravity for sharper cornering and better grip. With cells contributing to load bearing, overall torsional rigidity reaches 51,000 Newton meters per degree. For context, a tough Ford F-150 Raptor rates around 25,000, roughly half as stiff. The Xiaomi sedan even surpasses a Bugatti Chiron. A tech brand sedan, using its battery as structural core, achieves greater rigidity than ultra-premium supercars. This stiffness delivers real performance gains. An unyielding chassis lets suspension operate exactly as designed. Dampers react precisely. Tires maintain optimal contact during aggressive driving. The vehicle responds exactly as engineered because the base structure stays rock solid. And engineers tuned it to manage 1,548 horsepower from triple electric motors. Each spins up to 27,200 RPM, a production record. Typical high-performance EV motors peak near 20,000 RPM. Xiaomi's turn 35% faster, delivering more output from compact, lighter units. That's aerospace-level engineering. Without the Titan's metal structure and CTB integration, such power and speeds would overwhelm a standard chassis. But every element, material, process, design, and energy system was developed as one cohesive whole. Each supports the others seamlessly. What this truly means. With the SU7 Ultra, Xiaomi demonstrated more than one standout vehicle. They showed that rethinking everything from zero, without legacy constraints, can unlock the strongest advances. Using AI to create entirely new materials instead of refining old ones rewrites the foundation. Engineering a larger-than-ever casting system to replace dozens of parts with one redefines production. Integrating an inverted battery as structural element reimagines the car itself. Their Vision GT concept, promising around 1,900 horsepower and aero that would be illegal in Formula One, isn't fantasy. It's a glimpse of capabilities already running in their Beijing plant today. Titan's metal is in production. Hypercasting units output sections every 90 seconds. CTB vehicles are with owners now. Beyond one success, this sends a clear message to the entire industry. The age of building cars from hundreds of stamped pieces, joined by thousands of welds, with batteries added as an afterthought, is shifting. The future integrates material science, machinery, architecture, and power storage from day one. AI uncovers optimizations human experience alone might miss. This isn't simply an improved vehicle. It's a fresh philosophy on what cars are and how they're created, and every major manufacturer is watching closely. If you stayed until now, you're as passionate about this as we are. Smash that like button, subscribe for more, and enable notifications so you catch upcoming videos. We're diving deeper into cutting-edge tech because the coming years will bring rapid change. One final question for the comments. Could another tech giant like Apple, Samsung, or Google pull off something similar, developing a competitive car from the ground up? Share your thoughts below and let's discuss.